Right? So for the Riemann sum here, we've done left endpoint, right endpoint, and midpoint, right? And I also explained about the way how we regulate a midpoint is going to be the halfway between each. So midpoint, right, for n sub intervals is going to be the summation, right? Where the function here is we take the midpoint of each ith interval, the function evaluated at the midpoint of each ith interval and multiply with the delta x. Index runs from 1 to m. And then the midpoint for each ith interval is xi plus xi minus 1 over 2. So I introduced all this, right? And so at this point right here, generally speaking, a Riemann sum, right, left, right, or midpoint, or even any other point like that, basically we call that just as a general setup right here, a Riemann sum. Just simply we take the function value, right, evaluate it at some sample point inside of your first interval, first subinterval, and then multiply with delta x. We're adding that to the function value evaluated at some sample point in the second interval. Delta x multiplied with delta x, and so on up to the last one in subinterval. Delta x. So this is the Riemann sum that I call generally S sub n. It's a sum, right? And with n subinterval. So this is just a general Riemann sum formula over here. It's not necessarily the left endpoint, not necessarily the right endpoint, and neither the midpoint. It could be any one of them. Okay? And then in summation notation. In summation notation, yes, it's this. Here, the function at x, star sub I, multiplied with delta x. I index is 1, and two different ways how you write down the Riemann sum. Okay. All right, so we've done some examples. You guys got some good examples that we've done. And so in the end, everything we've been working through all started out from this problem. So we haven't found any answer to that problem yet. So that problem that I brought up as an introduction to the idea of Riemann sum here. Then what we have here is the function here, x squared function, right? Running from 0 to 1. So, again, as a reminder, the function here of x equals x squared, right? And then the interval here is going from 0 to 1. And initially I was asking, the very first question I was asking was, we want to find that area being shaded right under the curve, right? Between the x-axis under the curve and between those two given values of your intervals. Yeah. Right? So I label this the big area. But in the end, have we found that area? We haven't. Right? And then in that way, I explained about the left Riemann sum and the right Riemann sum. So why don't you guys actually calculate the left Riemann sum for this particular function here using this time I'm going to challenge you a little bit. So spend your time doing that. And start using your calculator. Go with L8. Okay? And yes, delta x can go. So 8 subintervals, right? Delta x is going to be 1 minus 0 over 8. Is what I'm saying, yeah? Right? So go ahead and approximate. So this is only an approximate, right? So the area, the real area that we still don't know, can be approximate by L8 here. Right? I started out the activity with L4. But now let's have you guys do L8. I do have a way to verify the answer. So go ahead and get your work done first of all. All right. Anyone got any luck? Yeah.
0.2734.
0.2734.
Yeah.
0.2734.
Yes.
Okay. All right. So that's the approximate. Now, so the work that came out should have been done among your steps, right? It should have been. So for this L8 here, what you did was should have been a 1/8 delta x, right? Multiply with, so the left endpoint for each of these intervals, the left endpoint here is going to be, so the function value at 0, that's the first left endpoint, right? And then the function at 1/8 plus the function at 1/4, right? Can you agree? Right? Plus yes, I agree the work gets tedious at some point. Also function at value at 3 fourths, right? And function value at 7 eighths. Right? That's the answer. Okay? But so in the end, is this the answer to our real area over here? No. It's still not the answer to the real area, right? So let me now do a graphical illustration for you on the screen. So this is the picture for that function f of x equals x squared, right? And we only need to look at that portion right there. We don't have to have we don't need to look at the entire area. So now I'm going to put in see the interval is indicated right here. Right? Those values I have here, that's the interval. So the start of the interval is at 0 and the end of the interval is at 1. Like that. So on the picture over here it shows, and it's hard to see a little bit, but it's right at the bottom from 0 to 1 again. Right? So that's set up like that. So with 8 intervals, with 8 sub-intervals, first of all, this is how I see the partitions. Right? So you guys see the partitions now? Right. So let me put it in a little bit of a closer zoom so that you can see a little bit better. Right? So the partition point is right here. Right? And I'm hiding away the actual values again, and that's what we need over there for our calculation. We should be able to write it down. But then with the graph, so now the picture here is going to look like, okay, so left Riemann sum is what we did. Right? So those are the 8 rectangles. Sound good? And so summing up, so each one of the delta x, right, multiplied with the height, delta x multiplied with the height, they give you the total accumulated area of these sub-rectangle areas. But it's always going to leave some gap, right, some white space again that we didn't reach the actual real area yet. See what I'm saying? No? So now think about that idea again. And when I started out with this problem, think about I was using only 4, so I'm going to change the slider a little bit. Initially, I started out with only 4 sub-intervals. And that was the picture back then, right? That was the picture over here. And then using, this is left endpoint, okay? And then you guys can see that picture, or either left endpoint or right endpoint. So let me hide away with that, but the right endpoint looks like that for 4 sub-intervals. And you also should have seen that picture before. And then with the midpoint right there as well. Okay, with the midpoint, I'm going to blend that in and put away the right endpoint. See, I didn't put the actual height here indicating, but you can see that the height of the rectangle rise is right at the middle of each of the middle tip of that the rectangle like that, right? So the idea now is that at this point, left endpoint, right endpoint is only as a choice here. So let's go back with left endpoint, but now when it was 4 sub-rectangles, then it was a lot of white spaces. And then we increase that to for today's activity that you guys just did, right? We increase the number to 8 sub-intervals, and you guys already saw that we squeezed out a lot of those are white spaces. You know what I'm saying? Or in other words, the accumulation of these sub-rectangle areas is getting closer to the actual true area. But still, in the end, we didn't answer that true area. See what I'm saying? All right. And so your calculation for this problem was indeed at the bottom of my page right here on the left-hand side panel. Okay? Left endpoint Riemann sum, right? Using 8 here. That's a point 2734, whatever that was on the bottom of that. See what I'm saying? Huh? Okay? So now I'm not going to waste your time around anymore with this. You guys kind of see where we're going with this. So the idea now is that you can see that what's the plan for improving the accuracy?
Use more.
Yeah, that's right. Just need more rectangles, right? Sounds good. But then more rectangles, that's the way how the picture is saying, but precisely speaking, you're going to need more sub-intervals, because the rectangles come out from breaking it down into sub-intervals, right? So we're going to need more sub-intervals. So how many more? There's no definite answer to that, right? The more, the better. The more, the better. So let's observe the picture over here. So on my picture, okay, I'm going to just simply slide the slider over here. You guys can see that right here, we are at 8, right? So I'm going to purposely slide. So what do you guys think? 16? Okay. We're going to go 16. So from 8 over here, I'm going to double that amount. You see that? See how the The rectangle is changed, then we got a lot more rectangles now. Okay? But then let's think of some consequences as we increasing the number of sub-rectangles. Or the number of sub-intervals here. So more precisely, yes, we want more sub-intervals, right? Or a different way of seeing that is more rectangles. But more sub-intervals means we're letting the number n here goes to infinity. Am I correct? Because n here is agreed to be the number of sub-intervals. N is out of the way. How do we notate the number of sub-intervals? Sounds good. So increasing n right there will get us there to the actual area. Because the plan right now is we want to improve the accuracy, right? And so right now, let me show that on the calculation right here with 16. Right now at n equals 16, right? We got using using L16 right here, the Riemann sum with 16 sub-intervals. You guys do the similar thing, but of course I'm not going to let you guys do that because it's going to take a lot of time for here. Let's have a look at what the result is on my table. On my board right here. So at the bottom part right here, see, I have that indication I showed earlier. We went from, so earlier when it was 8 sub-intervals, it was a 0.2 something. It's still on the board, right? 0.27. But now we went to 0.302, right? 0.3027, 34, 375. Okay. You guys are reading that part right there that I'm indicating? Right. That's the number that's highlighted right there. Okay. So that's the accumulation of these sub-rectangles. All right. So we came to that value, right? 0.30273, right? 4375. But then what's the real value? What's the real value? Of course, you guys we didn't have that yet. Let me tell you from my experience. Okay. So now, in my experience, I've seen this before. The real area here is a 1/3. Okay, or in decimals is a 0.33 repeating. Okay, that's the real area, and you will find out how we got to that later on. But just for this now, I'm talking out of my own experience and it's telling you that. So the real area here, I'm talking about the precise area. And so now, obviously, you can see using 8 sub-intervals, right? With left endpoint, we went at 0.2, close enough, right? 0.27 something, close enough. And then we came to 16, right? We got 0.302, and we keep getting better. That's why, yes, this is a good plan. Letting the number of sub-intervals increase. Okay. And we're gonna, get better to that idea. Okay. And so, in that way over here, let's think of a couple of consequences. Yes, as we desire more sub-intervals. So let me organize it this way. Improving accuracy means we want more sub-intervals. Okay, one more sub-intervals. And more sub-intervals is the same thing, means the same thing as increasing n. So mathematically speaking, I'm letting n go to infinity, positive infinity, right? And then that means the same thing as, and as a consequence, we got more rectangles. Sounds good? But then further consequence, don't you realize that? Think about the delta x here. Think about the delta x. The delta x itself is a formula. It's a b minus a, right? Over n right here. And then in our problem specifically, for our problem, delta x here is 1 minus 0 over n. You guys follow it? Okay? So for our problem here, delta x equals 1 over n. So what happened to this delta x? The width here, what happened to that width as n goes to infinity?
X equals delta x equals 0.
Yeah. Now don't say delta x equals 0, but delta x gets close to 0. It gets smaller and smaller. You guys see what I'm saying now? Okay. So this is right here gets to 0 as well. So it's back to that limits concept that we've been learning back in the calculus 1, right? It's the way it is because we always want to stay in that fixed window. Right? This fixed window. Now, as we keep dividing that into more sub-intervals and more sub-intervals, right? It's gotta be the way. It's gotta be like that, right? Each rectangle width, gotta get smaller and smaller. And of course, now we're dealing with the all equal sizes, equally spaced width. Okay? Sounds good. That okay? Okay. And so now back on the screen activity right here. Let me show you even a little more fascinating thing right here. So I was already kind of telling and cheating around with the wording that the area, the exact area is 1/3, right? So now let me really do that improvement on the board right here, I mean with the computer. So I only need to go up to 200 and look at how it changed the picture over here. Okay, let me even zoom it in. Let me even zoom it into a really extreme, hopefully extremely loud level so that you can still see the picture and how all of these rectangles change. So right now we're at 16 subrectangles. All right, so I'm going to change that. Okay. I'm going to increase. So you see how the white space is all keep getting squeezed out like that and squeezed out like that. Right now I'm only at 55. Right? And then I switch to keep getting better. So now the picture he can show this right in front of us. We don't see those white spaces that much anymore. And then we can keep increasing it. Now when we hit to about 200, seriously, it becomes like, and now let's look at the answer at the bottom right here. The reporting says 0.33. Right? It's now really close to the real area of that. Okay? And so that's the idea of what we're heading over with that. So just with a Riemann sum with that, right? Just with a Riemann sum, it's never going to be the real area. But then to improve, right? To get to the area, to get to the real area, right? Getting to the real area. What we need to do is the area here is that the Riemann sum with n subinterval, or for now we use left hand Riemann sum as a choice because if we let n, then we're taking the limits as n goes to infinity. See what I'm saying, no? Okay? And so, but now at this point, you guys can see that using a sum is the major idea right here. And so, let's for now put aside the worry about getting the precise answer. Okay, so in that way how I was talking about area, the only way to get to that area is we keep increasing. So, generally speaking, right, for that area right here, you can always express that generally as a Riemann sum. So the Riemann sum here is you can do that really with the left endpoint or the right endpoint. I mean, I started out here with the left endpoint. Right? You guys could also try that independently on your own time with the right endpoint or even with the midpoint. Right? So generally, it's a Riemann sum. It's n subintervals. And so to get that area, you get to take the limits for n increasing to infinity. Right? And so in that way, this is how I'm seeing the Riemann sum itself right here. Let's write it down a little bit. This sum right here, yes, in summation notation is that. And then f of some sample points, right, inside of each of your i's interval. Running from I1 to n, and multiply with the delta x in this case. You agree? Okay? And then this is not just only the area for our problem here currently. I'm talking about generally any area, right? If you want to approximate, if you want to get that precise area, you take the Riemann sum, right? Either the left endpoint or the right endpoint. And then in this case right here, we're going to, on top of that, we take the limits as n goes to infinity. We're increasing n. Right? So we set out with a finite number of subrectangles, okay, to have a successful formula setup. And then after that, right, we take the limit operations, but keep breaking it down further and keep breaking it down further. So that's just right here, just a theory, right? A theoretical process. Okay? That's how we get the area. Then again, like I'm saying here, in the earlier lecture, I mentioned that the Riemann sum itself, right? The Riemann sum itself is it's not necessarily to be always an area. See what I'm saying now? Or it's not always an approximate area. Because here we're just applying the Riemann sum to find an approximate of the area. The Riemann sum on its own is just that part of that definition right there. It's a Riemann sum on its own. It's not always area. But here, because it's easy to do a calculation on the area problem, so we introduce a Riemann sum. But area is only one application among so many applications out there. But so, and now let's look at the idea that we're investigating here. As you can see that, and I spoke earlier on the other board as n, right? When we take the limits, right, for n goes to infinity, then consequently the delta x here goes to 0. Am I correct? But go to 0 here, really, we're not finding limits, but the idea now it becomes so small. Think about an interval, right? From a to b, you're breaking it down to 4 subintervals, then you have a clear, big, easily seen interval. But if you're breaking that down to h, right, then your interval is smaller. Breaking it down to 16, right, your interval is smaller. You're breaking it down to 32, right? Now I would have a really hard time, right, making these points here. See what I'm saying, no? Okay, and then breaking it down to like 64, right? And even my pencil stroke right here is having a hard time fitting it. So the idea now is that as this delta x becomes 0, I'm just talking about becomes 0, but doesn't mean it equals 0. As this delta x becomes 0, then delta x really becomes a quantity that we call the dx right here. Okay, the dx differential. See what I'm saying, no? Okay, so you can think about this is the infinitesimally small change in x. It's so small to the point that when it's, you see when it's large, right? When it's a finite number of subintervals, and you can see it clearly it's a delta x. But then when it's so small, like that, right? The left and right endpoint really just come together. See what I'm saying, no? And so that's delta x will become dx, right? When we reach to that infinitely many number of subintervals. You got the idea? And then further on, think about this. Another consequence here. So let me make it real clear. See, as n increases to infinity, right? The consequence here is that delta x becomes the dx. And then the sample points in each of our subintervals. Okay, let's do that in a picture again. Interval from here, right? With 4 subintervals. And yes, you can see the interval is so clear, right? Sample point, midpoint, left endpoint, right endpoint, or midpoint, and you can see it clearly. Like midpoint can be easily found right there. It's a sample point. And then now, what if you're breaking it down to like 8 sub-rectangles, right? 8 subintervals, and midpoint right here. You guys agree? Okay, those are the midpoint or left endpoint or whatsoever. See what I'm saying, no? But now if you're breaking it down to 16, right? 16, then you have a harder time to find those midpoints or those sample points because the sample point is so hard to recognize. Okay? And so the idea now is that eventually when you increase n large enough, right, the sample points will make no difference with just any x value. Okay? And consequently it means, you see the function, you see in this part of the formula right now, the function becomes the function at any sample point in any interval. Now it becomes the quantity that's just simply f(x). Because the left endpoint, the right endpoint, really think about eventually it's going to come together just like that, right? And so even the sample points inside of that is going to just meet together at one point. So the height here is just f of x. See what I'm saying now? Okay. So I'm talking about the idea of becomes, right? Something that's infinitesimally small. So in that way, here's how we can modify the Riemann sum. So it's all like that idea right there. As n, right? The consequence of letting n go to infinity is that the delta x becomes the dx, right? And then the function evaluated at any of the sample points now really become the functions evaluated at x, at so many instances of x. Okay? And so now further, you see, so think about this expression right here in our Riemann sum. So that means function at the sample points multiplied with delta x generally becomes just simply f of x dx. So really it means the function's height multiplied with the infinitesimally small x quantity, small change in x quantity, the differential of x, right? And then the summation, we keep adding, but the summation has a limitation. The summation symbol has a limitation, starting index, right, with ending index here. But then in the end, when you keep letting at the end of the day, as you reach many enough, right, as you reach a large number enough of sub-intervals here, then the index is going to fail because there are too many of them. And as a matter of fact, you keep increasing the index, right? You keep increasing the number of subrectangles. So this notation here becomes the accumulation symbol. This symbol, yeah. Okay? That symbol right here means it's accumulation symbol. Accumulation. And then, yes, formally speaking, people call that the integration. Okay. And so, putting it all together, here's how we define it. Definition. Let's say that f of x is a continuous function. So at our level, we're always going to consider the function being continuous, right? The function that you can draw with an eye is a smooth curve without lifting your pencil. Or some interval a to b. Right? And so here's how we define it. Now with a function, right, you define what's called the definite interval. So first of all, let me write down the name. We call that the definite interval. This symbol over here on top of the function, right? With the dx. So f of x times dx here now has an index, and you guys already got the explanation where it came from. But then this definite interval over here is that symbol. You may have seen that before, right? But here's the thing: it's a different thing. You got this two in the indication right here that we're accumulating, right? We're accumulating. We're summing up from starting to the ending right there, right? So this definite interval, how do we define it? What does that mean to have that symbol? It means, first of all, we use a Riemann sum. We're breaking the interval a to b into so many sub-intervals. So, and then we multiply that. So we set up the Riemann sum from I from 1 to n. But then we are letting the number of sub-intervals goes to infinity. Right? And that's what the definite interval means. It's defined to be the Riemann sum, but we letting, on top of that, we're letting the number of sub-intervals increase to positive infinity. Okay? Now we can add it to our definition here a little bit better. The delta x here is simply b minus a, right, over n number. And then n is the number of sub-intervals. Side that interval from a and b. Right? That's the real true understanding of what an interval is. Right? We call it definite interval. So clearly speaking, you can still see that earlier when I talked about this symbol, I keep telling you out loud that it's only an instruction. Yes, it's still an instruction, and this is an indication finding the antiderivative of your function. But now with this thing, it's different. It's that symbol with the two lower and upper numbers over here. Okay, so this symbol here is indicating that we're taking the Riemann sum, we're taking the Riemann sum right in this setup, and then let the limits goes to positive infinity. Let that number of partitions, right? That number of sub-intervals increase to infinity, and that's what the definite interval means. Okay. So at this point, if anyone, when I'm talking to anyone about this, then I can always tell anyone that a definite interval, in the way how it is right there, and a definite integral is a accumulation, because adding up, right, summing up, it means we're accumulating values, right? Accumulating values, and we're accumulating infinitely many of them from the start to an end. We're accumulating every stripe here. So think about area. Think about area. That's interval right there for the function. See, your ds is just a small tensile stroke, but that's big enough. See, do you guys see a delta x here? You don't see a delta x, but really your tensile stroke makes some thickness, right? So the thickness is the delta x. Think of the delta x here as the thickness or the width. And then from there I draw a stripe up. It already has some area. You see what I'm saying now? And accumulating. So as I keep accumulating, right, we got more area. See, the height is being governed, is being regulated by the function. Am I making sense like that? So each one of the stripes here got a thickness dx, and the dx multiplied with the height is f of x. That's why the height is multiplied with the thickness dx, being accumulated, all accumulated from the beginning point A, right, to the ending point. We got that's why we use integral to apply that and find area. So area is only an application of a definite integral. And in the end, a definite integral on its own just means it's a Riemann sum, right? And we let the number of subintervals increase to infinity. Okay, sounds good with that. All right, so the symbols is similar to something you have seen, but still in the end, this is the symbol that we're having for the for the definite integral. It has nothing to do with antiderivative. Okay, so don't mix up with the two that right there that you guys learned.